Hello friends, we are back with our next video which is based on Henry's law. Henry's law deals with the solution of gas in liquid. So basically, what is this law all about? According to Henry's law, partial pressure of gas in solution is directly proportional to its mole fraction. As we can see right here, partial pressure of a gas is directly proportional to the mole fraction of the gas. अब इस proportionality constant को हटाकर equal to and a proportionality constant that is Kh, which is known as Henry's constant. So partial pressure of a gas is equal to Kh into mole fraction of the gas. Next, gases are soluble in water but up to very little extent, that is N very less than N. That means the number of moles of gas which is present in the solution is very less than the number of moles of solvent. So that N plus capital N is approximately equal to the number of moles of the solvent itself. Another important point to note here is ammonia and HCl gases are highly soluble in water as compared to other gases. Another formula which we have to remember is partial pressure is equal to mole fraction into total pressure. So these are some points about Henry's law which we have to keep in mind. Our next topic is vapor pressure. When a volatile liquid is in equilibrium with its vapors, then the pressure exerted by these vapors on the surface of the liquid is said to be vapor pressure. Vapor pressure depends on nature of the solvent, that is the liquid. It depends on temperature and also on the percentage purity. Next, we'll be dealing with Raoult's law, which is only for solution of liquid in liquid. What does this law state? When two volatile liquids are mixed to prepare a solution, then vapor pressure of a particular liquid in solution is directly proportional to its mole fraction. Now let us see the derivative of Raoult's law. Suppose we have two solutions A and B. Now according to Raoult's law, the vapor pressure of a particular liquid in solution is directly proportional to its mole fraction. So vapor pressure of A is directly proportional to mole fraction of A, and similarly vapor pressure of B is directly proportional to mole fraction of B. Or we can write that PA is equal to some constant into XA. Similarly, PB is equal to some constant into XB. Now, what is this constant? We'll see. So, the solution is made up of two components A and B. So, vapor pressure of solution will be equal to vapor pressure of A plus vapor pressure of B. That means PS equals to PA plus PB. Or we can write that PS is equal to P naught A XA, because PA is equal to P naught A XA, plus PB, which is equal to P naught B XB. So we get yet another formula here, that is PS is equal to P naught A XA plus P naught B XB. Now we'll see what the various terms mean here. PS is the vapor pressure of solution. PA and PB are the vapor pressure of liquid A and B in solution. P naught A and P naught B. Yes, this we need to know. This is the vapor pressure of liquid A and B in pure form. In pure form. This is important while solving numericals. In pure form, and as we know, XA and XB, they are the mole fractions of A and B in solution. They are the mole fractions of A and B in solution. Now we can yet derive another formula, as we know that mole fraction of A is equal to 1 minus mole fraction of B. So the formula was PS. The formula was PS is equal to P naught A XA plus P naught B XB. So we can write that PS is equal to P naught A. From here we are deriving it P naught A in place of XA, we can write 1 minus XB plus P naught B XB. On solving further, we get P naught A minus P naught A XB plus P naught B XB, or we get PS equals to P naught A plus P naught B minus P naught A into XB. While rearranging, we get this formula, and we have to see that this is in the form of a straight line equation. Y is equal to mx plus c, where y represents PS, m is represented by P naught B minus P naught A, and c is represented by P naught A. We have to remember yet another formula, which is YA is equal to PA, that is vapor pressure of A in solution upon total vapor pressure of solution, that is PS. So YA is equal to PA upon PS. Similarly, YB is equal to PB upon PS. Now we have to know what YA and YB actually are. YA and YB are the mole fractions of A and B in vapor phase. Mole fractions of A and B in vapor phase. This is another formula which will be used while solving questions. Now we have to remember one more thing here. It is if YA upon XA, that is the ratio of vapor pressure of A upon the mole fraction of A, is greater than the vapor pressure of B upon the mole fraction of B, then A is more volatile as compared to B. Sorry, I made a mistake here. YA and YB, they are the mole fractions. I refer to them as vapor pressure. So mole fraction of ratio of mole fraction of A in the vapor phase upon ratio of mole fraction of A in the solution. If it is greater than that of B, then we can say that A is more volatile as compared to B. One more important thing which we need to keep in mind for solving numericals is that 1 atmosphere is equal to 760 millimeter of mercury, or 76 centimeter of mercury, or 760 torr. Now we'll be dealing with some numericals based on the topics which we just studied. First question: the vapor pressure of two pure liquids A and B are 180 torr respectively. The total pressure of the solution obtained by mixing 2 moles of A and 3 moles of B would be. This is an MCQ. So the question provides us with, we have been given that the vapor pressure of two pure liquid, that means here we are talking about P naught A. So the P naught A is equals to 100 torr and the P naught B is 80 torr. Then the mole fraction is given as mole is given as 2 and 3 for that of B. So we can easily find out the mole fraction, which is equal to moles upon total number of moles. That for A is 0.4 and for B it will be 1 minus 0.4, which is equal to 0.6. So we have to find the vapor pressure of the solution. So PS, as we know, P naught AXA plus P naught BXB. So 100 into 0.4 plus 80 into 0.6, which is equal to 88 torr. So we'll tick that as the right option. Moving on to the next question, which states that the vapor pressure of pure benzene and toluene are 160 and 60 torr respectively. The mole fraction of toluene in vapor phase in contact with equimolar solution of benzene and toluene is. So we'll see how to solve. Here equimolar mixture is mentioned. That means we have to assume that number of that means the mole fraction of A and B, they are equal, that is 0.5 each. Next, P naught B is 160 torr, that for benzene. So we can find out PB, which is equal to P naught B into XB. So it comes out to be 80. Similarly, that for toluene, P naught T, that means the vapor pressure of pure toluene is provided, it's 60 torr according to the question, we can find PT, which is equal to 60 into 0.5, which comes out to 30. PS becomes 80 plus 30, which is 110. Sorry, we have to find the mole fraction in vapor phase. So we know the formula, mole fraction of benzene in vapor phase equals to PB upon PS. This formula was important as I told earlier. So it comes out to be 80 upon 110, which is equal to 0.73, and that for toluene can be found out by subtracting 1 minus 0.73, which is equal to 0.27. Next, we are going to talk about ideal solutions and non-ideal solution. Non-ideal solutions with positive deviation and negative deviation. Let's talk about ideal solutions. Ideal solutions are those which obey Raoult's law. Here the formulas are valid. PA equals to P naught A XA, PB equals to P naught B XB, and PS equals to PA plus PB. Then the non-ideal solutions with a positive deviation, first of all, they do not follow Raoult's law. The non-ideal solution with positive deviation, they show positive deviation from Raoult's law. That means here all the values are greater. PA will be greater than P naught AXA, PB will be greater than P naught BXB, and obviously PS will be greater than the sum of these two, that is PA plus PB. The non-ideal solution showing negative deviation, they show negative deviation from Raoult's law. Here all the values are less. PA is less than P naught AXA, PB is less than P naught BXB, and PS is less than their sum. That means PS is less than PA plus PB. Next, about the force of interaction. So there should be no chemical reaction between liquid A and liquid B. So interaction between A and that between B should be same as that on mixing them. And in the non-ideal solution showing a positive, the force of interaction between A and B on mixing the solution is less than that present among them individually, which implies that A and B, they escape easily, showing higher vapor pressure than the expected value. And we have opposite for the solution showing negative deviation. Here the escaping tendency of both component A and B is lowered, showing lower vapor pressure than the expected ideal value. Next, heat is neither absorbed nor evolved, hence heat change on mixing should be 0, that is delta H mix is 0 for solution showing positive deviation. Endothermic dissolution takes place, that means heat is absorbed or delta H mix is greater than 0 or positive. And for the solution showing negative deviation, exothermic dissolution, that means heat is evolved or delta H of mixture is negative. Now the change in volume change on mixing the solution should be 0 for an ideal solution. For a solution showing positive deviation, volume increases after dissolution, and for a solution showing a negative deviation, the volume decreases during dissolution. Now delta S of mixture, that means the entropy, is positive or greater than 0 for an ideal solution. It is positive or greater than 0 for a positive deviation showing solution, and same is for a solution showing negative deviation, that is it is positive. Next we'll see the graphs which are related to these solutions. This is the graph for an ideal solution. We have vapor pressure along the y-axis and mole fraction along the x-axis. This is P naught B. Here mole fraction of A is 0, that of B is 1. Here mole fraction of A is 1, that of B is 0. Along this line, PA is equal to P naught A XA, PB is equal to P naught B XB, and this adjoining line gives us PS, which is equal to PA plus PB. For a solution showing positive deviation from Raoult's law, we get a graph like this as shown in the figure. For a solution showing negative deviation from Raoult's law, we get a graph as shown in the figure below. Now coming to the examples of ideal solution, these are mixture of liquids having nearly identical properties like benzene and toluene. methyl alcohol and ethyl alcohol. For solution showing positive deviation from Raoult's law, we have a mixture of water and alcohol, and this is a kind of trick, you can say. Carbon tetrachloride with anything and solution of alcohol with anything will show a positive deviation from Raoult's law. Example of solution showing negative deviation is water and any inorganic acid, and CHCl3 and its solution with any other thing. That's all for today. We'll continue with colligative properties in our next video. Thank you.